Ladies and gentlemen, this is Alice. I'm really glad to, organize this iCANX talks. And this week we are, to have the start of December. Also, this will be the last month in 2023, so will be a highlight for a few things. So the first week of December, we'll have Professor Osamu Tabata from Kyoto University of Advanced Science. And next week, we're going to have three young scientists on this stage. And afterwards, the third week, we will have our big ceremony for our summary for 2023 of iCANX Talks. So let me first introduce this week's, the iCANX group. So we have a Professor Osama as speaker. We have three wonderful, panelists, and we have our beautiful challengers. So for Professor Awesome, everyone know him very well as because he was one of the pioneers in MEMS field. So Professor Awesome has, received his MS and PhD degrees from Nagoya Institute of Technology in 1981 and 1993. So that's a long time ago. Then it became a super pro. He joined the joined the Toyota Central Research and developed the laboratory in Japan. And after that, then he became a professor in Mexican universities. And then he moved to Professor Kyoto University in 2003. And now he moved to a new institute and a new universities. This was the kind of a new kind of universities, right? Yeah, Kyoto University of Advanced Science as a founder dean of a faculty of engineering and a grad school of engineering. And it also appointed to be executive vice president in this university. And it has been long time engaged with research in MEMS process and DNA nanotechnologies. And Professor Awesome was also go around the world. He has very deep, collaborations with Europe. And he also win many awards. Here I just highlight one is the IEEE EDS awards. And today he's going to tell us a story of bottom up and bottom up and top down going together to meet how to discover this micro and nano field. Professor Awesome, stage is yours.
Well, thank you very much, Alice, for your kind introduction. And thank you giving me this opportunity to talk about this topic. And I am very happy to have several very nice panelists and discuss after my talk on some kind of future of MEMS. So let me share my screen.
Yeah, please.
Yeah, now you can see my screen.
Yeah, comes. Good.
Okay, let me start. Well, as Alice introduced, there are two approaches, top-down and bottom-up, to make small-scale systems. And the top-down approach typically introduced by famous Richard Feynman in 1959 by the very famous talk entitled "There's Plenty of Room at the Bottom." And also the DNA nanotechnology was introduced by the bottom-up technology was introduced by Eric Drexler in 1986, and he wrote the book entitled Engines for Creation. And typical technology of bottom-up is DNA nanotechnology I will introduce today. And a typical top-down approach for making small system is MEMS. And I am very happy because I have been involved in both technologies, MEMS and DNA nanotechnology. And this is very happy for me because I could learn a lot. But still, have a feeling that there is a big gap between top-down and bottom-up. And in future, this area, the fused area of top-down and bottom-up, will have a great opportunity. And I do not have enough time to explore this area, but I expect you as a young researcher or young student, you can find a very nice opportunity in this area. So today I'd like to explain and introduce some of the history of MEMS and also some of the history of DNA nanotechnology and what kind of possibility could be exist in between those two technologies. Well, in 1982, I call this review paper, very famous review paper written by Carl Peterson, Silicon as a Mechanical Material. And I call this review paper a Bible of MEMS. And it was so nice, and I read many times this review paper. And this review paper has about 150 references, and I collected all the references and read through all the reference to papers, and I was say stimulated and inspired a lot. And this paper talking about that uh, integration of mechanical parts and electrical parts has a lot of possibility. And the typical silicon microfabrication technology, usually it is used for making transistor or LSI, can be used for making mechanical part as well, not only the electrical parts. And that the silicon microfabrication technology is versatile way to miniaturize very, very complex system. And as you may know, the LSI is a mass production, and it makes it possible to make very complicated micro complex system with low cost, so-called batch process, and because of the pre-assemble. You don't need to assemble many small components by hands or by other way. The automatically all the small components are assembled during the process. It's called pre-assembles. And the cards explained the silicon microfabrication technology has a lot of possibility to make the complex small system composed of mechanical components and electrical components. And because of his great contribution to the MEMS and also great contribution of the MEMS to the society, he got the Medal of Honor, IEEE Medal of Honor, and it is called the top medal of the IEEE. And some of the very famous researchers, Marconi, Fleming, Kalman, Shockley, those famous researchers all awarded this IEEE Medal of Honor. And Carl Peterson is one of that awardee. And it means MEMS has been recognized as a kind of established technology. And I am very happy because Carl got this IEEE medal, and it means MEMS was recognized by IEEE and many people as a kind of emerging and now established technology. When if we look back the history of MEMS, many people say in 1965 the first MEMS was presented, and it is something like this device. It's a resonant gate transistor, and this is a cantilever beam supported by this end. And you know this is a kind of MOS transistor, source, drain, and this is a floating gate. By applying the vibration, this beam can vibrate on the source and drain electrode, and this modulate the conductance between source and drain. So by monitoring the current through source and drain, you can detect the vibration of this cantilever beam. So this is so-called the first MEMS device, and this is the patented. The first word MEMS, MEMS, words appeared in this project application to the DARPA. And as you can see here, you can see the micro electrical mechanical system. This proposal is about the electromagnetic machines which utilize microgeometry field structures. And in this report, the first MEMS, first word of MEMS words appeared. And later, in 1987, Michael Gear was presented at Transducers 87. It was held at Tokyo, Japan. It was 1987. By two groups. One group is from UC Berkeley. You may know Don Fan, Yu Chan Tai, and Richard Muller. They presented this 3 gears train. And the diameter of each gears is about 50 to 100 micrometer, and thickness of this gear is about 2 micron. And the so-called very famous sacrificial layer technique was used, and it make it possible to this gear rotate along this axis. But in this time, the gears cannot rotate by themselves. It doesn't have any actuator. So by blowing the air to these gears, it can rotate, but it cannot electrically controlled. But this was shocked very many papers. And another paper, similar paper, was published, presented by another group from ATT Bell Lab. And those two papers was presented at the small room, about the 100 people can join. And I was there. I was attending that those presentation at the conference, and many people cannot go into the room. So many people are watching from outside of the room. And it was very hot room because many people are excited. I still remember the atmosphere of that presentation. And these presentations stimulate a lot of people. And many people start to think about this technology. This technology means silicon microfabrication can be used many different ways to realize something new. And the World MEMS was also appeared in the conference title in 1982, IEEE second IEEE Microelectrical Mechanical System Workshop. It was held at Salt Lake. And this workshop was started in 1987. And this workshop, originally, the title was this Micro Robots and Teleoperators Workshop. But later, the title was changed as First IEEE Micro Electromechanical System Workshop. And the in this first conference, the Jacobson gave a talk on micro electromechanical system. And in the second IEEE MEMS workshop, I also could opportunity to attend this second workshop. And after this workshop, I visited Kurt Peterson. That time in 1989, he already quit the IBM, and then he started the kind of startup named Nova Sensor. So I visited him because he who wrote that review paper was my god, and his review paper is my Bible of memes. So I really wanted to visit him, and I was very happy. So this young guy is me, and this guy is Carl Peterson. Now after that, I'm very happy to get to know him, and every time I meet him, we take a picture. And this picture was taken before the COVID, so it was 2020 January, and still we are friends and we are good. A little bit older, and my hair changed from black to white, and Kat's hair also changed from black and white, but still we are still active. Well, another topic, the same year in 1989, when at that time I was working at Toyota Central R&D Lab, and this year Toyota Motor organized very nice workshop as Toyota Conference. Toyota Conference every year different topics, and this year 1989, this Toyota Conference focused on integrated micromotion system, and this is considered as the MEMS. And a lot of famous researchers gathered at Toyota City in Japan and gave a talk. Some of them are still very, very active in this field, and I was this time just one employee of the Toyota Central R&D Lab, so I was working for the conference. I was something like a secretary for the conference, but as a secretary, I could attended this conference for 4 days, and it was also very, very exciting experience for me. And in next year, in 1990, the third IEEE MEMS conference workshop was held. And in this workshop, the scope says clearly about the broad application field of MEMS technology. So already this time in 1990, the people can anticipate it, the future of MEMS. It is, say, applications of MEMS are emerging in optics, fluids, chemical and biological processes, measurement and instrumentation, and robotics. So already people expect this MEMS technology can be applicable to many, many different fields. So that prediction came true, and now application field of MEMS is very diverse, from environmental monitoring, chemical analysis, medical diagnosis, transportation, including car or satellite, aerospace, communication, and computer, of course, robot and game controller, and so on and so on. And MEMS is now a key component for IoT, and also a key component to getting data and to provide for the AI. And the market of MEMS is continuously growing. As you can see, this shows the growth of the market from 2014 to 2020. As you can see, the growth is continuous and it's still continuing to grow. So what is the future of MEMS? I would say there are 4 directions. One is multi-dimension. Used to be the MEMS is a typical 2D structure, but now it's becoming more complicated 3D structures. And the second is multidiscipline. So it interdisciplinary devices. Used to be the device is mostly the physical sensors or physical systems, but the later the chemical components are integrated, and now many devices, MEMS devices, are related to biological components. So the field of discipline is broadened. And the third is multi-material, so diversity of a material. Used to be the MEMS is based on the silicon microfabrication. So basically silicon plus some metal which can be used for silicon microfabrication process. But later, many different metals or ceramics or polymers are used for MEMS. And now, even the biomaterials is used or integrated into the MEMS device. And the last, the multi-scale. So miniaturization is moving and moving and moving. Used to be the device size is about millimeter, and the minimum future size is about sub-millimeter or a few tens micron. But now micron is very common, and sometimes nanometer scale structure is used, and maybe in the future or already sub-nanometer, so atomic scale structure is integrated in the device as well. So I believe the MEMS future direction can be categorized in these four directions. Well, let me see another aspect, another approach for making small systems. As I said, in 1982, silicon as a mechanical material review paper was written by Carl Peterson, and exactly the same year, another paper, nucleic acid junctions and lattices by N. Seaman was published. And many people think this paper is the origin of DNA nanotechnology. And this is very, very interesting coincidence. The same year in 1982, two important approaches for making small systems was published. Let me see this paper. In this paper, and Seaman proposed this idea. You know, the DNA is a string and the component is four bases: adenine, thymine, thymine, guanine, so-called A, T, C, Z. And thymine and guanine can bind each other specifically, and adenine and thymine bind specifically each other. So CZ or AT can bind, but other combination cannot bind. But if you prepare four strands of different sequence of bases, this purple, blue, red, and green, and if part of the string, DNA string, is complementary. Complementary means the combination of CZ or AT. This combination is called complementary. If this part sequence of bases has complementary sequence of this blue DNA part, so CZ, DC, CZ, AT, AT, TA, CZ, CZ, then this string part and this part of the string can bind and form this helical structure. And this part has the complementary sequence with this part of green DNA. Then this part form another helical structure. So if you design all these four DNA strands as hybridized, and this binding reaction called hybridization can hybridize and bind and hybridize and form double helix structures with four arms. So just binding four DNAs, you can make this structure. The distance between two bases are only 0.3 nanometer. only 0.3 nanometer. So this length is about 3 nanometer. So this cross structure is about 5 to 6 nanometer. It's very, very small structure, but you can design the structure, shape, and form this based on the self-assembly process. And more interestingly, if you extend one arm, one strand as this, and extend this part as this, then design the base of this part and this part as have the complementary pairs. So these parts can make the hybridization as well. So with this way, these cross structures can bind each other to form 2D structure. And this idea can be easily extended to 3D structure. So something like crystalline structure can be also formed by this technology. And you may know that DNA is the genetic material for every creatures. Living things has DNA, but many of you may not know that DNA is now can synthesize. You can design the sequence of DNA. So for example, these 4 DNA can be designed by yourself, and you can send the design to the company which do the synthesis of DNA. Then after a week, you can get this DNA strand with this sequence in a small tube. So DNA is engineering material. That is very important point. So this shape is the same as this one. So if you see these two shapes, this shape is so-called holiday junction. It's one of the basic structure motif of DNA nanotechnology. And if you bind these two cross structures with this way, so here is one long DNA, and here is another long DNA. And this red one bind this part and then cross over to the another DNA and bind again. And this part is the cross structure I showed before. And this part is also the cross structure as before. And this yellow DNA is binding to one strand and then cross over again and bind to the another DNA, and the blue one as well. So with using this red, yellow, and blue DNA, these two DNA strands can bind each other, can connect each other. So this idea can be extended further to make larger scale structures. In 2006, another idea was proposed by Paul Rosamond, and it is called DNA origami technique. And this is one of the techniques to scale up the nanostructure. In his proposal, typically he used the long DNA, the length, circular length. This long DNA is a circular DNA, and the total circumstance length is about 2 micron. And the number of DNA bases is about 7,500 bases. And this is taken from the virus. It is not a synthesized engineering. It is taken from the one of the virus, but it is safe. And what you need to do is to design the small, about 200 or 250 small and short DNA. And these shown by red color, this short DNA is designed by yourself. This long DNA can be folded like this to form any shape you want to make. And the red short DNA you designed should bind part of this long DNA and fix the folded structure, folded long DNA structure to fix. So all the short DNAs, about 200 or 250 short DNAs, can bind everywhere of this shape to fix this shape. So this reaction is very easy to do. Just mix this long DNA, this is called scaffold, and short DNA, this is called staple, and adding some buffer solution plus metal ions, typically magnesium, in a small tube and heat up about 90 degree, because at that temperature, 90 degree, all double strand helix structure is debind. So they separate each other. So they are free. Then slowly cool down the temperature from 90 degree to room temperature within a few hours. Then automatically self-assembled these structures. The next slide shows the video of this self-forming, self-assembly process. So this is part of the long DNA scaffold, and these are the short DNA you design. And long DNA start to fold, and short DNA start to bind and hybridize to form the double helix structure. And finally, all the short DNA is bind to this long DNA, and the long DNA is folded as you designed. So based on your design, you can form any kind of shape with using this technique. So in 1982, the first idea of DNA nanotechnology was proposed, and 2006, DNA origami technique was proposed. And there are many other ideas and techniques were proposed, and now very complicated structure with size of a few tenths nanometer can be fabricated. For example, this kind of very small base structure can be formed, or this kind of structure also can be formed, or this is a kind of open closed structure with using two shells. So something like shell structure can be also made. So now DNA nanotechnology has a lot of techniques to make a lot of different structures. And people now start to think about how to use these DNA nanotechnology to make something useful structure for our life. So MEMS is a typical top-down technology, and DNA nanotechnology is a typical bottom-up technology. But still, they are not fused well. So there are several, not several, there are many opportunities in between. Well, let me introduce some of my research with my colleagues toward that area, but I have not succeeded yet. Still many things I need to do, but I'm working on that part. So today I'd like to show two examples. One is body-on-a-chip device, typical MEMS device using top-down technology. And the another one is nanosensor, which use DNA nanotechnology. Well, body-on-a-chip is a device to integrate the several mechanical components such as pump or a valve, and also integrate the cells from the body. And in this demonstration, we cultivate two different cells taken from the body. One is from the heart, the other is from the the liver. And we demonstrated how this body-on-a-chip device works, and it's very promising. Some people say organ on a chip. Organ on a chip is the same concept which cultivate the cells from organ or body on a chip, and one of the main target of this organ on a chip or body on a chip is drug development or pharmaceutical application, because it takes a long years to make the new drug, and also it costs a lot to make new drug, and many of the approaches attempt to find the new drug is failed. Only a few of them succeed to be available for the to be commercialized. And to reduce this time and to reduce the cost of developing a new drug, this organ on a chip or body on a chip is very expected to play important role. Organ on a chip is a chip which cultivates one type of organ on a single chip. Now already many different organs succeeded to be cultivated on a single chip. Brain or heart or kidney or liver or blood or muscles. But as you know, the body is a kind of system, and those organs are not independent. They are connected by fluid, for example, blood or the other the body fluid, and they are in a sense communicated. They are interacting each other, so they are communicating each other. So just cultivate one type of organ on a single chip cannot mimic the body, cannot simulate the body. So we need to cultivate several different organs on a single chip. So the interaction between organs is very important to mimic the body functionality. So to demonstrate the idea of the importance of cultivate different organs, different cells from different organs on a single chip and connect them by small channels and make it possible to communicate by circulating the media between the organs. We demonstrated this chip. In this chip, we integrated cell from liver and cell from the heart. And we made this together with pump and valve systems. So this is a kind of fluidic system. And we demonstrate the importance or effectiveness of this integration of different organs on a single chip by using this drug. And this drug is already known as this is very effective. This drug is very effective to cure the tumor of the liver. But this drug chemically processed in the liver and make the side product, make some other chemicals, and that chemicals, if it's transferred to the heart, it damage the heart cell. So it's called side effect. It is already known, so this cannot be used for the drug to cure the tumor of the liver, but we intentionally use this drug to test that by applying this drug to the device, the liver can survive, but liver cell can survive, but heart cell is damaged we demonstrate this by using this chip. So here is the heart, and this is the liver, and the chemicals. This doxorubicin is processed in the liver, and the byproduct is flowed to the heart cell, and these byproducts damage the heart cell. So this is very toxic side effect. So we demonstrated that with using this kind of integrated system, we can, prove that this this drug cannot be useful for the human. And if you only use liver cell on a single chip and test this drug, you cannot find this side effect. So we demonstrated the importance of the integration of several different organs on a single chip. And one of the future one of the challenge we have to meet is to detect what kind of chemicals exist in the body-on-a-chip device. Because, as I said, the byproducts damage the heart. So what kind of chemicals exist in the flowing in the chip is very, very important information for evaluate the effectiveness of the drug. But the system body-on-a-chip has very small amount of chemicals, so it's not easy to real-time monitoring those chemicals. To monitor the small amount of chemicals in such kind of small system, one of the approach is to make a very small sensors, so-called nanosensors. So one of the approach we tried is using surface-enhanced Raman scattering principles. Surface-enhanced Raman analysis is very well known. If you irradiate the small gold nanoparticle, typically 10 to 100 nanometer, this is typically silver or gold, then the very strong Raman resonance and strong electromagnetic field is generated along these gold nanoparticles. And if you place the two gold nanoparticles, then more strong electromagnetic field is generated in between two gold nanoparticles. And but if this small gap we call nano gap with size of 1 to 2 nanometer, and if excite these gold nanoparticles by a certain wavelength of light, then very strong electromagnetic field is generated here, and if small molecules attach to this, then the Raman scattering light is generated, emitted from this structure. And this Raman scattering light has information about what kind of molecules attached to this nanogap. So from the spectrum of this Raman scattering light, you can determine what kind of materials exist in the solution. And this is extremely sensitive, so you can detect only one or a few molecules attached to this nanogap. And this principle is very useful because it is label-free. You don't need to chemically process the material you want to detect. No pre-process is required. And it is non-contact measuring principle and non-destructive. And you can apply this method on-site. So you can use this as a handheld measurement equipment. And also this also applicable to aqueous aqueous samples. So liquid samples can be used. So this is very good combination with the body on a chip device in future, not now. And how to make that gold nanoparticle pairs? We call this dimer structures. This is gold nanoparticle dimer. One of the very straightforward way is to use electron beam lithography. Fortunately, my previous university, Kyoto University, had extremely expensive electron beam lithography machines. It's cost about $8 million US. And one of my colleagues, now he is a professor at the Kobe University, make a small groove on the silicon surface and then assemble two small gold nanoparticles in this groove and to make the gold nanoparticle dimer. This gold nanoparticle is about 100 nanometer. And by applying one of the base of DNA, for example, guanine or adenosine, then the very specific spectrum can be appeared from by measuring the Raman scattering light. So it means that this structure, even one pair of gold nanoparticle dimer can detect very small amount of molecules, single molecules. And this is very low cost, and this is a very sensitive method to detect very small amount of materials and also characterize what is the material is. But the problem is this method costs a lot. And what we need is much low cost fabrication technique with high yield and high reliability without using electron beam lithography. So what we think is we can use DNA origami technique. So we made this kind of structure by using DNA origami technique. So this is typical size is about 80 nanometer by 50 nanometer. And the two DNA nanoparticle, nano DNA origami structure was assembled together to make this T-shape. And from the surface, for example, 30 adenine strand. So 30 adenine is connected each other and extend from the surface. And this kind of extension was placed here, here, and here, and here. On the other hand, gold nanoparticles surface is modified. Modified means another type of single-strand DNA is attached to the gold nanoparticles. In this case, 30 thymine strand is attached to the gold nanoparticles. As I said, adenine and thymine can bind specifically each other. So by mixing this T-shaped DNA structure and gold nanoparticle whose surface has thymine, then gold nanoparticles can bind on this T structure to form this shape, this structure. Then after purification, this structure is deposited on the silicon chip. And then this DNA structure is decomposed. Decomposed means disassembled, removed from the surface. Then only the gold nanoparticle is left on the surface. And then these are the gold nanoparticle dimers left on the surface. Some of the monomers remain on the surface, but most of them are dimers. Some of them are multimer, but relatively high yield of dimers can be obtained by optimizing the several experimental parameters. As you can see, monomer and dimer and multimer. The dimer has about 70% yield is achieved. And with using these structures, we use as a test solution, bipyridine, 4,4-bipyridine is used. And in case of the concentration is 1 millimolar, then you can see the clear spectrum which originated from these chemicals. When we decrease the concentration 1,000 times lower, so 1 micromolar, still we can see the peak of originated from this 4,4-bipyridine. So in this concentration, the number of molecules attached at this nanogap area is about one or a few molecules. So it proves that this is extremely sensitive sensors. So we think not yet, but we are thinking to this kind of very small nanoscale sensor that can be integrated with body-on-a-chip device to detect what kind of chemicals component exist and flowing in the body-on-a-chip device. And that allow us to evaluate the effectiveness of the new drug for the diseases. Well, let me move the final part. So as I said, the MEMS technology based on the silicon microfabrication has several unique features which make it possible to make very complex small system composed of mechanical and electrical, and also now chemical or biological components can be integrated with very low cost and high yield. And also DNA nanotechnology has several unique features. I did not explain everything, but for example, the DNA nanostructure itself can be designable, and you can make 2D or 3D structure. And it is self-assembled process. So you don't need to use that kind of very expensive electron beam lithography technique. Just using the tube and the pipette and mixing and heating up and cooling down, you can make very small structures. And the surface of DNA structure, this is also very important because you know the sequence of bases, DNA, of this DNA structure. And those sequence information can be used as address of on the structure. So you can specify the point to be addressed. For example, you can bind another nanocomponent on this DNA nanostructure. So this DNA nanostructure can be used as a kind of platform to assemble another nanoscale structures precisely with sub-nanometer resolution. So you can arrange several different for example, particles with different type on a single DNA structures by addressing them very precisely on the surface. And also this DNA nanostructure can be bind each other. So much larger scale structure can be possible. So this uniqueness of DNA nanostructure has a lot of possibilities. I started the MEMS research about, well, I started in 1981. So already more than 40 years, close to 45 years, I have been involved in MEMS. And I started the DNA nanotechnology about after I moved to Kyoto University, so it was 2003. So already I spent about 20 years in DNA nanotechnology. But DNA nanotechnology is very, very tough technique. But I believe that the DNA nanotechnology has a lot of potential, and of course, MEMS technology has also very good potential. And I believe by combining those two fuse those two structures, those two technologies, top down and bottom up, we can make structures with diverse materials. So diversity of material can be realized. So many different type of nano materials can be assembled on, for example, MEMS device. And diversity of scale, because DNA nanostructure can handle sub-nanometer scale structures, and MEMS device can handle up to centimeter to sub-micrometer or a few tens nanometer. And the complexity of structure also possible. Both MEMS and the DNA nanotechnology has possibility to make the very complex structures. So by combining, by fusion, these two technologies, we have more opportunity to make something new system. So far, I cannot succeed it yet. Unfortunately, at the beginning, when I started the DNA nanotechnology, I thought it's very promising, and I can realize I can achieve very great results in a few years. But actually, it was not so easy, and I'm still struggling. But I believe in some time, maybe you can make the big progress in that area. So as I said, this area has a lot of possibility, and I would like to see some of you can make a great progress in this area by fuse the two approaches, top-down MEMS and bottom-up DNA nanotechnology. Well, I would like to finally thank my collaborators at Toyota Center R&D Lab, Bismarck University, and Kyoto University. And I did some research at Freiburg University. And I especially thanks to Professor Koji Sunagano. Now he is a professor at Kobe University. And Professor Hirai, Yoshikazu Hirai, is the lecturer at Kyoto University. And Professor Kamei, he's now New York University at Dubai. I would like to thank all those close collaborators, especially. And I would like to thank several funding agencies, including Japanese government, many industries, and the foreign government as well. Well, thank you very much for your attention, and I would like to happy to discuss some of the aspects I speak today. Thank you very much.
Okay, great, Professor Osama. It was a very nice talk, and very nice, class. I think most of the people in maths field learn a lot from the talk. So let's move to our panel discussions. Yeah, let me first introduce, our panels. And today we really have big panels. Where's my slides? Okay, right here. Okay, let me first show that. Okay, there. We got too many stop sharing now. Okay. Let me first introduce our panelists here. And today we have a great panel. Actually, is for Professor Awesome. I think the panelist from Zhuo Qingyang from Shanghai Jiao Tong University. Actually, he got PhD in Shanghai Jiao Tong, and then he moved to Japan. Yeah, he did a few years study in Japan. She is quite a few familiar with the Japan Society of MEMS. So Zhuo Qing did a lot of work for initial MEMS, power MEMS, and nano MEMS, and now he's kind of young talent in Shanghai. I think got several titles, so we're proud of that. Zhuo Qing, welcome. And our next, panelist is Zhu Qingwang. Yeah, Wang-san is from Sichuan University. Actually, Wang-san I think I spent more than 14 years in Japan, right? Yeah. got study in Kyoto University and then working in Tohoku University, and did a lot of nice works there. And then he moved to Sichuan University as a special professor, and now as a super PI for leading, I think it should be 100 people's team like that. So it's a quite a big team, and did a lot of work in MEMS field. Also, as doing a great achievement for the commercialization in this field. So welcome, Wang Sang. And our
Thank you.
third, panelist is Yungang Jiang, yeah, from Beihang University. Yungang also spent many years in Japan. Yeah, got a PhD, I think, Tohoku University, right? And works in Japan. And okay, Yonggang, yeah, your microphone, please mute. Okay, yeah. So actually, Yonggang did a lot of work, nice work, specializing in Tohoku University. That time I visited Professor Isachi. I think I met Yonggang that time too. Yeah. So back to Beihang and did independently for about 10 years. Now she's a super professor there. And tonight we also have our challenger as Fang Yexing as a PhD candidate in Peking University, and she is going to challenge Professor Awesome. Yeah, let's move to our panel discussion. I think as usual, our questions start from Fang Yexing. Yeah, Yexing, please.
Of course. Thank you, Professor Zhang. And now I can ask a question?
Yeah, sure. You can.
Thank you so much, Professor Tabata, for your nice and impressive presentation. I have only one question. It's about the scaling effects. In MEMS, due to the scaling effects, there are some physical phenomena are very different from the macroscope world, such as dimensional effects of forces and the surface effects on microstructures. So I was wondering, for DNA nanotechnology, it is a bottom-up technology. It's also a molecular assembled. So are there different rules when fabricate a nanoscaled devices? And should we avoid or take advantage of these differences? Yes, that's my question.
Well, yes, the scale is very small, and also the stiffness, for example, it's very soft. But the interesting thing of the DNA nanotechnology is because you can design the combination of binding bases. The 4 bases is connected each other by using hybridization and the other method. And for example, if you think about make the one load, one strand, but how to arrange the DNA bases, the bending stiffness can be controlled because of the molecular, the force between molecules can be somehow controlled by designing the different sequence of bases. So and that force is dominated by the very small let's say the atomistic scale binding force, for example, hydrogen bonding or ion bonding. So usually the material property is sought in larger scale. MEMS, in most of the MEMS materials, the material property is fixed. If you use silicon, the material property is already known, fixed. But in case of DNA, by designing the base sequence, you can design the material property itself. So that is very uniqueness point. One of the unique point of the DNA nanostructure. So that is rely on very controlling the phenomena appeared very critically appeared in such kind of small scale device, small scale structure. I hope I can answer to some of your question.
Okay, great. Actually, this was a hard, questions to answer. Yeah. Bottom up and top down, also different materials and a different kind of interface. Yeah. So, great. I think, Professor Awesome, you really, in this field for how many years? 40 years, right? Yeah.
MEMS field
Oh,
40 years and the DNA
yeah.
20 years.
Yeah, more than that. So you already try a lot. Yeah. So beautiful. Yeah. For questions, okay, Zhu Qing. Yeah, please.
Me? Okay. Thank
Yeah.
you very much. Tabata Sensei, it's very honor to attend your presentation. So as a OB from Tabata Lab, it's very honor, and I learned a lot from Tabata Professor. Especially, so I saw the presentation. I know how to do research. For example, DNA origami. Maybe I attended your lab maybe 10 years before. So it's just the middle tab. So I think I want to introduce to my students, many students here. My students attended the meeting. So you work hard for the research. I understand, very hard.
Yeah.
So my question is, now I work in China as a leader for the research group, and I think a lot of research topic for my young my group for the teacher or the student. So my question is, someone I think a lot of researchers in Japan, the challenge for the new research field, for example, honor professor obviously use for me is the new researcher in some research fields. But I know some very famous Japanese researcher. They told me work hard on just one research field for a long time. For example, 30 years, 40 years, they have a good result. So, but some of them is the basic research. But for the MEMS, is application research. So, how do you think for the new researcher or for the young researcher, how to decide the research field to continue for a long time or challenge for the new research field? How do you think of that?
Well, I think it depends on the individual characteristic. Some people really wants to go focus on one field and go deep and deep and deep. Well, let me tell this story. When, as you said, MEMS is a kind of technology to integrate several different technologies into one and make something new functionality using some new structure. But most of us, or almost all the principle is already discovered by someone and very well known in each subject. But by integrating several different principles or structures, you can realize something new. But in Kyoto University people likes to focus on one field and go deep and deep and deep and find something very new. But it takes time and it's very hard. And I say this is the analysis approach. But my approach to do MEMS is not analysis. I not go deep and deep, but instead I realize I notice some new effect already known each field, but I interested in some principles and then integrate them to make something new. I say this synthesis approach. And I like this approach. I'm not the guy do analysis approach and go deep. I'm a guy to integrate something and then make something new. And when I moved to Kyoto University, because most of researchers, professors in Kyoto University is a person doing analysis approach, but I'm not. So I was thinking, I may not fit in this university, but so I present when I had an interview to Kyoto University professors, I present my approach, my analysis, my synthesis approach. And if they don't like me, or if they don't like my approach, they will not take me. But if they like me, maybe 10 professors doing an analysis, but one professor doing synthesis could be okay. So I present my approach, and finally, luckily, they accept me. So I continue my approach. So it's up to you. If you like the analysis, then you should do analysis. But if you like synthesis, then do synthesis. If you like
What
synthesis,
a beautiful answer.
yeah.
I like that one.
If you like synthesis, do not go analysis because it's not your characteristic.
Mm-hmm. Yeah, I like your answer too. Actually, this is really depends on the individuals. Also depends on the field. You know, some field may need you long time focus on, you know, one things to go deep. Some field was running really fast, right? You need to get kind of more skill to synthesis, you know, many things together. Like normally many people talk about the multidisciplinary, right? Yeah. So about you got multidisciplinary, this kind of synthesis, easily, you know, maybe move to this new field, no directions. So I think, you know, this work is very good. So yeah, next time is talk about, okay, if you are analysis people or you are synthesis people. Yeah.
Thank you very much. Thank you very much.
Yeah, very good. And, you know, Zhuoqing, please.
Okay. Hi. Very nice talk from Osamu Tabata-san. I'm very glad for your slide for the many conference about the MEMS. In my teaching classes, and I also talk about the very famous MEMS conference. It's the MEMS, HV MEMS transducers, HV sensors, and it's very interesting. And I looked at many old pictures from you. It's very interesting and happy. Yeah, and I have one small questions. I know you are a very famous professor and is a pioneer for the MEMS and invitations of the etching solutions TMAH. And in my classroom, I also speak these stories about you.
Oh, thank you. Thank you very much.
Yes. And in my group, my students, I have some students. I also to talk about how to balance, because some students want to do the researchers is about because your project is from the different, some from the industrial and some from the government, and how to balance the industrial or the commercial applications and the innovations researchers. It's like the Professor Wang's questions and the different students and how to choose the research topics for the students. Some students want to do the industrial applications research, and your project is also about the innovations researchers and how to balance this the different aspects. Thank you.
That's also very difficult question to answer. Well, I would say the application-oriented research, if the application-oriented research based on some very conventional technology, it means everyone can do, but the company asks your group or your student to do so. Maybe it's okay, but it's not so interesting because why me? Why I need to do? Any other person can do. But I think
centers is.
I think that not, at least for me, it's not happy. But well, I tell you another story. Okay, I tell you another story. Why I moved from company to university.
Yeah.
I quit Toyota Central R&D in 1996 and moved to Ritsumeikan University. As you may know, company has money and the company has facilities, but the university I moved in, no money, no facilities, but freedom. Freedom is there. Okay? At company, if you, I have several ideas and I want to start that research, but at company, if I want to start something new, I need to persuade my boss. I need to persuade my boss why we need to do this. There are two very effective way to persuade my boss. Okay, one is already that company, competitive company doing this research, so we have to start now. So this is one. Another one is this is very, very promising because if I do this, then this. So it will be no risk. It's very, very, very promising. It's both are not attractive for me because if someone already started, why I should start?
Yeah.
If very if you can say, if you do this, then result is this and this and this. If it is very predictable, no risk, then it's not interesting. So for me, attractive research topic is nobody do yet. It's new, and also it's very risky. But I can believe it could be okay. It could be successful, but not 100% sure. But I believe I could succeed. But another people cannot believe that. But I believe. So that's why I want. So
Yes,
but
I
those,
can.
yes, you can. So those two way to persuade is not interesting to me. So that's why I moved to university. At the university, I have freedom. I can do everything, but I need to earn money by myself. But I have freedom.
Yes.
So I like that. But what if student like the stable position and the money and satisfied with using existing technology to apply something? If he like or she likes, it's okay. It's up to them. So it's again depend
Okay.
on individual personality.
Yes, I
Yeah.
totally agree with you. I see that, most of the people's, who like the challenge, they really move. Yeah, always move. So if they really don't like the challenge, of course they choose something, Yeah, see, I think Professor Awesome just now says that if someone already did that, why I should repeat? Right? I don't need to repeat anyone else, right? I need to do something in my mind. Yeah, that's the kind of professor's job. I think professor need to, add educated your students in this way, then we can get a lot of kind of talent, right? A lot of brains work. Otherwise, our brains all in the same. No way. Yeah. Okay, Yonggang, how about you?
Okay, very wonderful talk, Professor Tabata. Nice to meet you again. Yeah,
meet you.
I have a very
Thank you.
short question. During the past 40 years, you have done a lot of excellent MEMS devices. For example, I remember you do a lot pyroelectric imager sensor in 1998 or 1997. And you also do the DNA origami, and you do body on chip. You tried different fields. And I like the pyroelectric imager sensor very much because it's a monolithic sensor in 20 years ago or 23 years ago. So what's your favorite research or what's your proudest research you have done during the past 40 years? Thank you.
What did you say? What is my what?
What's your favorite research you have done during the past 40 years?
Favorite?
Your favorite research, your own research.
My favorite? Oh, I never think about that. What is my favorite? Well, you didn't mention that, but I also doing research about the so-called moving mask technology. It was started when I was with Megan, and that time I had an opportunity environment to use synchrotron. So have you heard about the LIGA process? LIGA process uses synchrotron X-ray.
Yes, I know LIGA process.
Yeah. And I started to work on the LIGA process, but LIGA process usually the substrate and the mask. But in my case, I move the mask against the substrate, something like this. So during the exposure, I move the mask intentionally. And by controlling this movement, the structure fabricated on the substrate is not vertical, but that has the sidewall can be curved. So the curved structure or pillar structure, not the needle structure, very different type or complicated structure can be fabricated by using this moving mask technology. And when I started this research, I started make my own experimental setup from scratch. I programmed the control system and everything I did by myself. And it was very tough, but it was very, very exciting. And that technology was extended to not only the X-ray exposure, but also the UV exposure. And the UV exposure moving mask machine was commercialized by a company. And that time was very hard because that time I moved from company Toyota to Ritsumeikan, and everything was new. No facility, I started from scratch. And it was very hard time, but it was very interesting and exciting time for me. So I cannot say which one is my favorite, but I like that time. That time was one of my excited research.
You like that freedom, right? Yeah. You
Yes,
can
yeah.
you have freedom to do what you want, Yeah. Make all these kind of beautiful things by your hands. Yeah. I think now Ritsumeikan has the best facility. I visit Professor Satoshi Konishi a few years ago. Yeah, I think it almost have everything.
Yeah. Actually, the Satoshi-san, Konishi Sensei, and I joined the Ritsumeikan University exactly the same year. It was 1996. So we together with another professor, Professor Sugiyama, and Konishi and me, three worked hard to establish the facilities.
Yeah. Now, the Ritsumeikan now almost have everything. I think it is a big harbor there, right? For maps. Yeah. So nice. Actually, I have a question for you, Professor Tabata. You were two kind of, yeah, you did say some important things. Like Zhuoqing says that, UTMAH, fabrications, etching, is one of the beautiful kind of process in the class. Yeah. So you many conferences you involved, MEMS, transducers. Also, the new conference now it's not new. It's one of big flag conference too. Our NAMS, right?
Yeah.
You didn't
NAMS.
mention that. Okay, you should. Yeah, please.
Well, let me briefly speak about
Yeah.
that by sharing the slide.
Sure. Yeah, welcome. Because next you are going to have NAMS conference and Kyoto. Yeah, Professor Osamu is general chair is going to host this. Not only
Yeah.
the beautiful place, we'll have a lot of kind of new things in this conference. Zhuoqing next time must mention this. The best conference in the NAMS conference. Okay.
Yeah. Wait a moment.
Yeah,
Okay,
for
this
sure.
one.
Because I'm one of the founder too. Yes,
You
please.
see,
Yeah, I
well,
see that.
yeah,
Yeah.
the MEMS conference, NEMS, not MEMS, Nano Micro Engineered and Molecular System NEMS conference will be held May 2 to 5, 2024 next year at my university, New University, Kyoto University of Advanced Science. And please join this conference. I think the general chair is me and Professor Yokokawa, Kyoto University, and several other universities work together with me. And this is our university, and at Kyoto, it's in the city, so it's very convenient to come. And this is the overview of the university. Our building is here. You cannot see exactly, and we will have the conference in this new building for engineering. Okay, let me skip the video. And maybe I don't need to explain about Kyoto. It's very convenient from where in the world, especially from China. It's very close. It's from Beijing about 2 hours or 3 hours. It's very close. And the place is in the city. So from Kyoto Station, it takes about only 20 minutes. So just by subway ride, you can reach the venue. But please submit your papers, but please wait. Do not wait the acceptance, because May 2 to 5 is the golden week in Japan. It means the hotel costs will increase very much. So book now, and then submit paper. So deadline will be December 18th, so soon. So please submit your paper, but book the hotel first, and then submit your abstract. And I'm looking forward to have you all who are attending this iCANX seminar. You are the person to submit the abstract to this NEMS conference. I'm very much looking forward to see you all at Kyoto. Thank you very much.
Yeah, okay, great. Actually, I'm really looking forward to this conference because this year the transducers was in Kyoto. I'm unfortunately got my leg broken. Now I'm looking for my second chance to go to Kyoto. I think
Yeah, you should
NAMS is
come.
the best. Yeah, NAMS is the best conference. Actually, Professor Osman and me work on this conference since I think 17 or 18 years, right? Yeah. We
Yeah,
really start that many, next year will be 19 years. So this conference is focused on micro, nano, engineering, and molecular, the molecular systems. So like today, we talk about top-down and the bottom-up. So this conference is the right match for top-down and bottom-up.
yes,
We also have,
exactly right.
Yeah. We also have several kind of awards for the students, and for the young scientists, though, we also have one kind of special award is microfluidics, right? Yeah,
Yes.
for Ho Award. So it's a beautiful conference, a beautiful place. So yeah, be sure come to Kyoto, next May and reserve your hotel right now. Yeah. So to save some money. And also get a beautiful chance. Okay, thank you, Professor. Yeah, awesome. Yeah, it's really, really great, discussions. And I'm thinking time fly almost, to the last. Let me, go to the part to conclude this. Yeah, so yeah, for our top down and bottom up discussions, yeah, so also people's here. I think when Professor Awesome jump in the field and, in the later of 1980s, like Fang Yexing, she not, born that time, right? Yeah, she born about 1980, 2000 or sometime. So yeah, so this was really a long time story, and also it's a hard work story and evaluation story. I think we appreciate to see, Professor Awesome say that, do research work not in one skills, in several skills, right? You maybe you're analysis person, maybe you are another kind of a, synopsis person, maybe you can build up another kind of superstar session too. And so this was kind of a platform for everyone. And we proud of we have a Professor Awesome today. So as regular Professor Awesome, this is a certification for you. I will hand to you next May, okay? And the next conference. Yeah, thank you so much. And yeah, next week
Thank
we're
you very
going to
much.
have yeah, next week we're going to have our young scientist session. Behaven was, win the Young Scientist Award of iCANX last year, and another two young professors was Matthew and Junjie was superstars in, similar areas too. So you invited three of them to deliver talks. After next week, we'll have a, December 15, we will have a summary of this year. So let everyone keep, looking, and iCANX. So I think it will be a beautiful, kind of platform for everyone. And also we have many things for you and the next year. So yeah, let's see you next week on iCANX on Friday. Yeah. Okay, that's the end of today. Okay.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。 创造奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。像我一样飞越最高山岗。
これまでの AR